Hi, I'm Rich with insideHPC. We're here at ISC 2018 in Frankfurt, Germany, and we have a special presentation, some exciting news coming out of Europe and the Exascale efforts. So I'm going to hand it over to Hugo Falter from Partec.
Hi, Rich. Thanks so much. We have here, for this exciting news, you said we have here the representatives of 4 sites. May I introduce them to you and to your audience? So we have, starting here, we have Jean Gonneur representing CEA. We have Jean-Marc Denis representing Atos. We have Bernhard Frohwitter representing Partec, and we have Thomas Lippert representing the Forschungszentrum Jülich. And the exciting news is, you might have heard about Mousquetaire.
Oh, yes.
We use that name again for an undertaking in Europe to jointly develop European technology for HPC and beyond. And I would like to ask the participants what their motivation is, what they have in mind, what the goal is, and then we can discuss about it. Maybe we start with our friend Jean from CEA.
So, you know probably that CEA has always been, for its creation more than 50 years ago, involved in high power computing. It has always been, HPC has always been a stake for whole CEA mission, defense, energy, fundamental research, biology. And with that goal, we start in 1996 a very important program in order to have an independent access to this technology. So it was called the Terra program. I have been conducting this program for 14 years until its success in 2010, where for the first time we built the Terra 100 machine, which was the first petaflop machine ever designed and built in Europe. So today, we are first looking at what the European Commission is announcing. I think we will come back on that. And in order to answer to the challenge of the Commission, all of us, the 4 here, have decided to make a group in order to answer together to this challenge.
Thank you, Jean. Thomas, from the Forschungszentrum Jülich, the Jülich Research Center, what is your motivation to be a Mousquetaire?
Okay, so my name is Thomas Lippert. I'm leading the Jülich Supercomputing Center. So we are a center that is a provider of supercomputing time to various, let's say, groups in fundamental, in applied sciences and for industry all over Germany. So we are a German national center, but we are also one of the European providers within the framework of the Partnership for Advanced Computing in Europe, the BRACE partnership. So we are not only provider, we are also doing own research within the center. It's a big center and probably one of the biggest civilian centers in Europe, having a large computational science and engineering activity there. And on top of that, we are very much pursuing the goal of creating technology for high-end computing and in the last years for exascale computing. Those projects we have initiated are called the series of deep projects, the dynamical exascale entry platform. And within this project, we have created new architectural ideas, let's say called modular supercomputing. And within the modular supercomputing, we want to join and we want to go with our friends from the Mousquetaire-Group, that is the group here, that wants together with different expertise that we find with our, let's say, different contributors to create a truly European supercomputing technology, ranging from the processor up to the architecture and having a very clear, stable integration strategy, along with the necessary software to operate it. That's what fascinates me with the Mousquetaire-Group.
Thomas, now we heard the two research. Now we go to the industry.
Thank you very much, Hugo. We are very proud to be part of the 4 Mousquetaires. So, first, because it's French novel, and second, because there is an ambition through the Mousquetaire project. This is to deliver to Europe European technology for exascale computing. So obviously, Jülich and CEA are the reference public partners for reaching this goal and this ambition. And Atos, as #1 supercomputer company in Europe in terms of installed power, just look at the last top 500 list, you will see the numbers. On #4 in the world, we want to partner with the most advanced supercomputing centers, and we want to deliver top technologies. We want to co-design with our partners the technologies for exascale computing at the service of European science and European industry. So we are extremely proud and ambitious for Europe through this project.
Yeah, thank you very much, Hugo. You have heard a lot already about the motivation and the determination of the group and what it's going to do. So permit me a few words concerning the history of Partec into this. Partec started about 20 years ago and was in HPC all the time. The software we produce is middleware and is the management of such ambitious computers. In 2010, and that's probably the most important part of the story, at least for me and for Partec, Thomas approached me and said, Bernard, we have to do something. We will see in probably 10 years huge machines, and I didn't believe, Thomas, that you coined the term exascale already, but there will be 1,000-time petaflops. Today we call it. But, and that's an important point to me, we can't just do it bigger and bigger and bigger, what we are doing. And frankly, by the way, what I believe the Americans are doing to try to reach exascale. We cannot just make thousands of nodes and make them as fat as possible. And then because that the next super generation, we must invent, we must find a new architecture. And there is an idea that he said, I have since so many years about it, reduce that to practice. And since then, we are developing what today is called path toward exascale, the hardware, the software, and then my last 10 sentences, perhaps, I'm also extremely proud because in autumn last year, we had been approached by these fabulous gentlemen with a proposal to form a group, organize a group, to go for this ambitious goal and provide European exascale. And that's what I'm extremely thankful to also to partners. And we are totally engaged and motivated to get there, and I'm absolutely convinced we will. And I believe our American friends will learn the lesson that Europe, believe it or not, takes over the lead, the driver's seat in this technology, and has something in its hands that will succeed, whereas, as I believe very frankly, the US will not succeed with the monolithic, homogeneous monster computers. They will not.
Thank you, Bernard, for that statement. So, Rich, you heard 4 enthusiastic partners, CEA, Jülich, Atos, and Partec joining forces. Developing European technology for HPC. The modularity is the basic architecture for that. How do you see this approach in comparison to other approaches around the world? Bernard, you mentioned the US, we know China, we know Japan. Maybe a short statement from the participants, how they see our European approach in comparison to what we at least know from these countries. Jean-Marc.
As Bernard has extremely well explained, you have two ways of approaching exascale computing. The first way is the brute force approach, reaching exascale with a monolithic approach, big fat nodes, focusing on the lean pack, focusing on extreme double precision, lean pack numbers. This is very good, very interesting. And this is, let's say, the first step. But the real difficulty is not there. The real difficulty is in real day-to-day activity for day-to-day applications. And we know that with the rise of big data, artificial intelligence, IoT, with a massive flow of information going on the way, simulation and application will change, will dramatically change over the next 5 years. So the flow of information, the flow of data, the applications will become extremely complex over time, with some parts working the classical way with double precision, solvers, that kind of stuff we have known for the last 50 years. New way of analyzing data. So this is graph analysis, this is deep learning techniques. On all of that, it has to be mixed in single applications, in a very complex data flow that has to be hidden to the end user, to the developers. They cannot have PhD in biology and in computer science. They are biologists, they are whatever, physicians, scientists, but not experts in computer science. So the first complexity is to provide them a very complex architecture, mixing different modules, and this is a concept of modularity that has been well explained by Bernard, hidden to the end user. Top of that, a very complex software layer that will bridge the different modules all together with the transition of the information, of the data, of the application into a single development layer, an application workflow. And this is the ambition of Mousquetaire, to create a modular production environment for exascale class applications, not exaflop lean pack, exascale class complex applications, hiding the complexity at hardware, on software level, at application level, at data level, to make in order that the end user can focus on science or not on developing the techniques or the expertise for using those computers.
Thomas, could you again explain what you had in mind?
I think modularity is, so to say, the acronym for the architecture. Let me put it into a larger context. First of all, we do not have just one element that is innovative. We believe we have three innovative elements in our approach. One basic one is Europe will go for an own processor. There is the EPI initiative led by Jean-Marc Denis, where the goal is to have a very powerful in terms of memory performance processor very early in order to, let's say, overcome this real devastating gap of memory performance that we see today. The user or the computer center pays 10 times as much of energy if you have only 1/10 of the required memory performance. That's what we have today, yeah, for memory-intensive application. The second element is also a very important issue. You have to have a stable technology. Remember, we are going up to exascale. Exascale is thousands, 10,000s of nodes. It's millions of cores. It needs control functions. It needs to have a cooling technology that's unprecedented. There are only very few companies in the world that can do that. It's very clear to us that we are very keen to have a partner in like Atos that has proven with the Sequana architecture and with the coming Sequana 2 architecture that they can really do it. And on top of that, using this architecture, we can build very stable entities we call modules. One of the entity will be a standard cluster system because it has to be very versatile, universal, doing the job that we know from cluster computing on a very large scale. Another one will be a module that is scaling up to an unprecedented performance, again based on the Sequana technology. This is a module that goes to the Exascale. Now let's combine both modules through the Parastation software. This combination of the two modules allows to let's say, use and run program parts that are better performing on the cluster to run on the cluster, and to use those that are better performing on the scalable element we call booster to run on the booster. These are two different elements. And the major point here is to make is if we can get those running in parallel, which we have shown already with a machine that you can find, for instance, in the infamous top 500 list, there we know then we have a system, one computer consisting of 1, 2, 3, 4 modules that is an optimal thing for a given code, for a given problem. Sometimes the problem will only run on the cluster. Sometimes the problem might best run only on the booster or on an FPGA element or in the future on a quantum computer. That's what we want to achieve.
Thank you, Thomas. I would like to come to Bernhard once again for the comparison of the approach to get to Exascale. Here we talk European technology, we talk Atos with Sequana, Partec with Parastation, the modularity. We talk about the two famous research centers with all their applications and their experience. But the approach, Bernhard, how do you compare this European approach to what they do in the United States, in China, in Japan? What is the big difference?
Well, yeah, I believe one of the main differences is that systems that we closely monitor and observe in the United States, China, and Japan, which, by the way, are kept extremely. The architecture is not published, but one can conclude from accompanying materials what is going on. And I believe that one of the problems will be that such computers which are focusing on fat nodes, which are heterogeneous. The nodes themselves are heterogeneous, but the whole computer then is totally homogeneous. An assembly of thousands of fat nodes, that this has no future. I believe it will not reach exascale, I said this already, but it has also no future because you will not be able to add further modules to such a monolithic system, which I believe more and more turns out to be one of the biggest disadvantages. Think about the quantum computer. That could be a model and should be a model that you integrate with existing network and infrastructure. They will not be able to do it, but the modularity is just designed for this, that you put in more and more new models that come up through scientific endeavors, through technology advancements, and that is something that this technology is wide open for, apart from the enormous flexibility to act and react on all the different codes which modern applications come with, and that you somehow should handle without overly burdening the user. The user should be an important part of this and should be able to handle his application in such a machine. Certainly not with seamless, that's not where we are, but with much less engagement and burden on the user. And that is one part. The other part, which I also really would like to mention, is, again, it's not only that the modularity will provide, and provides already, as already shown with the Eureka project and now also with the ULS project, the existing modular computers. Modularity also means you do it less costly, much less costly. The requirement for highly sophisticated nodes is much less, which also frankly means enormously less dependency of Europe on US chip technology, with all the encumbrances that come if you are dependent on a state which is a friend, but which believes that certain obstacles to free trade and free flow of goods and also ideas should be directed in under a certain motivation. Something should come first. Also having that in mind, that in Europe we have something which is better, cheaper, more efficient, and makes us independent of the United States, not to speak of China or Japan. So there are coming an enormous amount of advantages with such technology, with the modularity. And I should add, the modularity comes on two levels. One level, we call it the macro level. This is his invention. But there is also, maybe we call it micro level, that is the Sequana board. The Sequana board in itself is also modular. So that is a combination which also makes it enormously unique and extremely promising for the future.
Thank you, Bernhard. I have finally a question to Jean. Jean, we know that you especially and CEA are on the first line of HPC users, but also HPC specialists and a driving force for the European idea. Now, with the Mousquetaire-Group, with this news which we share today, I have the feeling as if something would come together, join forces you had in mind since a very long time. Am I right? It's a kind of fulfillment today?
Well, that is true, that after the success of Terra 100, which is coming, I want to tell that very clearly, it's coming from a concept which is the co-design. We realized this machine first time from nothing, because during 10 years, we developed a very strong co-design with the industrial bull, mixing on one side the machine experts, and on the other side, the expert of the application, the specialist of the interface between application and the machine. And one we learned at that time that the main problem was not to design a machine for a given purpose and a given time. It was to design a general architecture for several machines, even several architecture, because the more and more complex things we have to solve, the longer will stay the software. And we are facing the real problem is facing the fact that we are developing very complex software that will last 30 years or more, and that during this time we will see 5, 6 machines, and surely also different architectures. So this is what we learn. And knowing that, and thinking to what we will do at the next step, speaking of this step, Exascale step, we knew that it will be more and more complex, first. Second, that we will have to solve more and more different applications, even applications that appear tomorrow and that we never thought yesterday. And here I jump on this Thomas concept of modularity. You know, it's for that reason that we need modularity. If we want to win share of market, we have to answer to new application, and to answer to that, we have to be very modular, to be able in a very small amount of time to answer to the question of this new application. And so we need to be able to propose different solutions. But proposing different solutions starting from zero is indefinitely costly. And so to do that, we have to start from a basis which is open, which allows a lot of modularity. And it's what we have begun to develop with Atos, thinking of that challenge at the beginning. And this has to be extended now to a lot of new activity, to a lot of new applications. And we have to be able to guarantee that using modularity, we will not lose all the advantage that we had before. And this can be only done through co-design.
Thank you, Sean. So, Rich, if you would ask me now what is Mousquetaire, I would say if these four entities, these four partners, CEA, the Jülich Supercomputing Center, Atos and Partec, join forces with European technology, using the modular architecture and do it in a co-design, then I think this is the translation for the modern Mousquetaires. And we want to help, I really mean it, the world in a way to get cheaper, with less money, less energy to Exascale and help the users for that. But I'm interested now how you from outside Europe see this Mousquetaire European approach.
Well, thanks, Hugo. Thanks for the opportunity to hear about this today. And I applaud you for your ambition. I know how hard Exascale is going to be. I mean, I hear about it all the time in America, right, from scientists like you guys. My question is more about how you're going to organize, set goals, milestones, and measure success. I don't know if who would like to take on that question?
Well, it allows me to answer to another question. We are public lab first, with the help of large industrial. And as public lab, we are answering, we are not making our own challenge, we are answering to the challenge given by our government and today by the Commission. Naturally, you can think that maybe we have helped a lot in preparing the decision of the Commission, but today we are facing a political declaration of the Commission. We set up a very ambitious program for the 2022 and beyond. So we are answering to that. We estimate, and it's a common thing to see in a newspaper, to see that France and Germany are the engine of Europe. We think that we are able together, France and Germany together, with their very large public lab, with their strong industry, to answer to this challenge, and that we are the best one to answer.
Yeah, maybe I can also add a few things. This is, of course, a very good question. How do you, to be ambitious is one thing, but how do you reach your goals? The milestones. One milestone was last year when we showed for the first time in Denver the first modular supercomputer of the world, which is called Eureka. I think it was listed with 4 petaflops or 3.4, something like that. In the meantime, it reaches 6 petaflops. And in Jülich, there is already the next generation underway. The cluster is ready of the Jules computer, which will have 75, 80 petaflop. The booster, the accelerator thing, is immediately starting after the cluster is taken over, which is a matter of days, the last few weeks. Jülich was busy with Atos and Partec to take over the cluster. And I believe the European Commission, especially the DG Connect, the responsible people in the European Commission have understood that maybe a little bit surprisingly, even to them, that Europe has something in the making, and you simply, in quotation marks, you simply have to continue this path to exascale, build the next machine, the pre-exascale machine. Is it a machine which has more than 100 petaflop? Frankly, I believe that is not a problem. Modularity with the software, with the middleware, and then just go and continue and build the exascale machine. I believe the Commission has understood this. I'm, of course, not a speaker at all for them, but my personal impression, also talking personally to the leading people, they have understood it, and that's what they want. And those are the milestones. So to summarize, 2 milestones already, one already done. The second one is in the making, half of it is done, and that's the path to exascale for Europe.